Always looking to get smart fast, right?
Hope so.
Today, we're taking on a topic that's, well, super important in the world of AI. How do we actually understand what these increasingly powerful systems are doing? Think about AI making recommendations in medicine or finance.
Yeah.
Wouldn't it be great to know why it's suggesting what it is?
Absolutely. These advanced AI models, especially the ones using deep learning, they can feel like black boxes, really. They give us an answer, but the reasoning behind it, often hidden.
Yeah,
And that lack of understanding, it can make it hard to trust them, hard to use them effectively.
exactly. So for this deep dive, we've got a comprehensive survey paper. It's called LLMs for Explainable AI, a comprehensive survey.
Sounds like a mouthful, but it's important stuff.
It is. Consider this our roadmap, right? To understanding how these cutting-edge language AIs, large language models, LLMs, are being used to, shine light on those previously mysterious AI systems.
So our goal today is basically to break down this paper's key ideas, make it make sense, even if you're just sort of familiar with basic machine learning concepts.
Yeah, demystify it a bit.
We'll look at the problem they're tackling, the smart approaches being explored, key discoveries, limitations, the whole picture. Ready to jump in?
Definitely. This is a really critical area. I mean, as AI becomes more involved in our lives, especially in sensitive fields, we need this. We need what's called explainable AI, or XAI.
XAI.
It's not enough for an AI just to be accurate. We need to grasp why it's accurate, and also, importantly, where it might stumble.
Okay, let's unpack this whole explainable AI or XAI idea then. In simple terms, what are we talking about?
Okay, so think of XAI as, well, a set of methods, really. Tools that help us understand the how and why behind an AI model's decisions.
Making it transparent.
Exactly. It's about making these AI systems more transparent so we can see the logic they're using. The big aims here are, building trust in AI, ensuring there's accountability when AI makes decisions, and also helping make sure these systems align with our ethical values and, frankly, what people actually need.
So the core challenge is this black box issue we mentioned. Why is it such a big deal that we can't always see inside these AI models?
Well, look, without that transparency, it's tough to really trust the AI's judgments, isn't it?
Makes sense.
Imagine a doctor using an AI to suggest a treatment. If the doctor can't understand why the AI is recommending that specific treatment, they're naturally going to be cautious, right?
Yeah, absolutely. You wouldn't just take its word for it.
Precisely. It's the same in finance. If an analyst doesn't know how an AI is forecasting market trends, they'll be less likely to rely on those predictions for, big financial decisions.
Okay.
This lack of understanding can lead to less effective use of AI, make it really difficult to figure out who's responsible if things go wrong. And it can even hide potential biases within the AI that we really need to know about.
Right. It's not just about the AI getting the right answer. It's about us being able to follow its reasoning, see if that reasoning holds up, or if maybe there's a flaw it would otherwise miss.
That's it.
So how do these large language models, LLMs, come into play? How can they potentially help explain things?
This is where things get really interesting. LLMs are, they're incredibly skilled at understanding and generating human language, right?
Yeah, that's what they do.
So this ability, this fluency with natural language, makes them a really promising tool for XAI. They can essentially act as a kind of translator.
A translator, how so?
They can take the complex, often numerical or abstract outputs of other machine learning models and turn them into explanations that are, well, easy for us humans to understand. Plain English explanations.
Okay, can you give us a simple example to, illustrate that?
Sure. Let's say we have an AI that looks at X-rays. Maybe it's detecting potential problems in lungs.
Okay.
Instead of just spitting out a label like abnormal, it could use an LLM to explain why it thinks it's abnormal.
Ah,
The LLM might say something like, I detected patterns in this region consistent with opacity, which is often linked to pneumonia. It highlights specific patterns, explains the link in simple terms.
so the doctor gets context.
Exactly. The doctor can understand the AI's reasoning, compare it to their own knowledge, and have more confidence in the assessment. It's like the AI is showing its work,
That makes a lot of sense. So this survey paper, LLMs for Explainable AI, it really dives deep into how this is happening across different areas.
Exactly. Yeah, this paper gives us a really broad view of all the current research into using LLMs for XAI. It looks at the various methods people are developing, how they're trying to figure out if these LLM-generated explanations are actually helpful and accurate.
Yeah.
It's key.
Right.
It covers the current challenges, the limitations, and where these techniques are actually being used in real-world applications. Think medicine, finance, even in processing language itself, like text analysis.
And future directions, too.
Yeah, the authors also point out where things need to go, like making the explanations themselves even more interpretable, maybe more automated, really focusing on what the user needs.
User-centered.
User-centric, exactly. And involving people from different fields, working together multidisciplinary approaches.
Okay, so we've got a good overview of XAI, why LLMs are exciting here. Now, let's dig a bit deeper into the core problem this field is trying to solve. We've touched on it, but let's make it crystal clear.
Right. So the fundamental problem, as we've sort of danced around, is the sheer increasing complexity of AI models, especially deep learning.
Gotcha.
These models can have, millions or even billions of parameters, all interconnected. The way they process information to arrive at a decision can be incredibly intricate, almost impossible to trace manually.
Like a giant tangle.
Yeah, it's like trying to understand how a giant tangle ball of yarn works just by looking at where a single strand pops out at the end. This complexity directly leads to that lack of transparency.
And this lack of transparency isn't just like a technical curiosity, is it? It has real practical consequences.
Absolutely. This opacity, this black box nature, makes it really hard for users, especially people who aren't deep ML experts, to understand and therefore trust the decisions these AI systems are making.
Yeah, trust is key.
It is. And like we said, without trust, the AI is less likely to be used effectively or even used at all in some critical cases.
Right.
You also run into serious issues with accountability. If an AI makes a significant error, how do you figure out why? Who's responsible if we can't follow its reasoning? Plus, and this is a big one, without transparency, it's much harder to spot and fix any hidden biases that might be lurking in the model, biases that could lead to unfair outcomes.
So the main goal of XAI, and specifically using LLMs for XAI, is really to bridge that gap, build user trust, provide those crucial insights into how the models work.
Right.
All without ideally making the AI less effective, like less accurate. It's about getting both performance and understanding.
That's the balancing act, exactly. We want AI models that perform well and are understandable. And go back to our earlier examples, it's about empowering that doctor, right?
Yeah.
Helping them truly understand the reasoning behind a treatment recommendation so they feel confident acting on it. Or enabling that financial analyst to interpret an AI's market predictions so they can make informed decisions.
Yeah, we understand the problem, the why. Now let's talk about the how. How are LLMs actually being used to solve it? This paper outlines some key methods. Can you break down the main approaches for us in simple terms?
Sure. The paper basically highlights three main ways LLMs are being used to boost explainability. The first one is through what they call post hoc explanations.
Post hoc, like after the fact.
Exactly. You got it. This approach involves analyzing why a specific input led to a particular output after the machine learning model has already made its prediction. It's kind of like being a detective, right? Trying to figure out what happened after the event occurred.
So the AI makes its decision, maybe flags an image or makes a prediction, and then we use an LLM or some other technique powered by it to try and understand how it got there.
Precisely. And within this post hoc category, there's a distinction. There are global explanations, which try to explain the overall behavior of the AI model, like what general rules or patterns has it learned across all the data.
The big picture view.
Right. And then there are local explanations, which focus on just one single specific prediction. They highlight the particular input features, the bits of data that were most important in reaching that specific result.
Okay. Global for the whole model, local for one specific instance. Can you give us another example to make that difference clearer? Maybe not medicine this time.
Okay. Let's imagine an AI that predicts email spam.
Right.
A global explanation might reveal that overall the model has learned that emails containing words like free, prize, or using excessive exclamation marks are generally more likely to be spam. That's a general rule it uses. Now, a local explanation for one specific email being flagged as spam might point out that this particular email contained the phrase, claim your prize now, and had like 10 hyperlinks. Those specific features triggered the spam classification for that email.
Got it. Global is the general strategy, local is the reason for this specific play. And the paper mentions some specific techniques here, right? Integrated gradients, LIME, SHAPAP. What are the core ideas? Sounds technical.
They can be, but the core ideas are understandable. There are different ways to investigate the why after the fact. Integrated gradients, IGE, basically tries to figure out which parts of the input were most influential. Think of slowly changing parts of the input and see how much the output changes in response.
Like turning knobs to see which one affects the outcome most.
Sort of, yeah. LIME, that stands for Local Interpretable Model Agnostic Explanations, focuses on understanding a single prediction. It works by slightly tweaking the input data around that specific instance and seeing how the prediction changes. It's like gently poking the model to see what makes it wobble on its decision for that one case.
Okay, perturbing the input locally.
Exactly. And Shapley additive explanations. This one comes from game theory, actually. It tries to assign a specific value, a contribution score, to each input feature, showing how much it pushed the prediction towards the final outcome.
So for the spam email, SHEP might say the phrase claim your prize added like a 20% probability to the spam score, and the hyperlinks added another 15%.
Precisely that kind of thing. Gives you a breakdown of contributions.
Okay, that gives us a good handle on post-hoc methods. Looking back, what's the second main approach the paper talks about?
The second main approach is intrinsic explainability. Now, the key idea here is different. It's about designing the machine learning models themselves, sometimes using LLMs as part of their actual structure in a way that makes them inherently explainable right from the start.
Ah, so instead of explaining after, you build it to be explainable.
Exactly. Instead of trying to understand a black box after the fact, you try to build a see-through box, or at least a box with some clear windows.
Makes sense. How does that work in practice?
Well, think about how we understand a single system with clear rules. The rules are the explanation. Intrinsic explainability tries to bring some of that clarity to more complex models. A good example is using LLMs that have attention mechanisms.
Attention mechanisms, I've heard of those.
Right. They're often used in language tasks, like figuring out the sentiment of a piece of text. Is it positive, negative, neutral? These mechanisms allow the LLM to essentially highlight which words or phrases in the text were most important for its decision.
So it points to the evidence.
Exactly. If it classifies a review as positive, the attention might light up on phrases like excellent service or really love the product. Those highlighted words act as a built-in explanation.
That's pretty neat, making the model's focus visible. The paper also mentions something called chain of thought or COTI reasoning here. What's that about?
Ah, yes, chain of thought. Code reasoning is a technique mostly applied through prompting, where you encourage the LFM to break down a complex problem into a series of smaller logical steps. It basically thinks step by step out loud.
Like showing its work in math class.
Pretty much. It makes the model's thought process much easier to follow and understand, and often leads to better results too.
Okay.
And there are refinements on this. Guided CUDA templates give the LLM a predefined structure to follow. So for that math problem, you might tell it, first, state the knowns. Second, write the formula. Third, calculate.
Providing a scaffold for its thinking.
Right. And then there's REACT, which stands for reasoning and acting. This is even more dynamic. The LLM doesn't just reason. It can take actions, maybe query a database or interact with a simulated environment, see the result, and then use that outcome to inform its next reasoning step.
Oh, wow. So it's learning by doing, almost, and explaining its reasoning as it goes, like a robot exploring a maze.
Exactly like that robot example. It reasons, I should go left, acts, goes left, observes, hits a wall, and reasons again. Okay, left was wrong, now I should try right.
That sounds incredibly powerful for understanding complex interactive tasks.
It is. And just one more point on intrinsic explainability. The paper also mentions using LLMs to generate explanations that then train other models.
Oh, using explanations as training data.
Yeah, the idea is the student model learns not just the task, but also the reasoning behind it, becoming more interpretable itself. And, crucially, there's work on checking the reliability of these intrinsic explanations. Are they factually correct, logically sound, especially vital in medicine or law?
Right, the explanation needs to be right, not just exist. Okay, so we have post hoc, after the fact, and intrinsic, built in. What's the third main angle?
The third category is human-centered narratives. This one really focuses on the user. It's about presenting the explanations from ML outputs in a way that is most understandable, useful, and trustworthy for the specific person receiving them.
So less about the technical details and more about communication.
Precisely. It recognizes that even a technically perfect explanation might be useless if it's full of jargon or doesn't connect with what the user actually needs to know or how they think. It's all about building trust through clear, relatable communication.
Tailoring the explanation to the audience.
Exactly. It involves understanding what information the user needs, when they need it, and how to present it effectively. The paper really stresses involving the end users, doctors, financial analysts, customers, whoever in the design process,
How do they do that?
through things like interviews, focus groups, usability studies, surveys, really digging into what makes an explanation helpful and trustworthy for them.
So instead of just dumping raw feature importance scores, the AI might try to weave a story.
Yes, that's a great way to put it. Create a narrative. For example, if an AI predicts a patient is at high risk for hypertension, instead of just listing factors like cholesterol 250, family history, yes,
Right.
an LLM could generate a narrative for the doctor. Based on the patient's elevated cholesterol levels, documented family history of hypertension, and recent weight gain, the model calculates a significantly increased risk. These factors commonly contribute. See, it connects the dots in a more natural way.
Much easier to grasp. And you mentioned counterfactuals earlier.
Yes, that often falls under this human-centered approach, too. Counterfactual explanations tell you what could have been different. For instance, if a loan application is denied,
Yeah.
a counterfactual explanation generated by an LLM might say, if your annual income had been $5,000 higher, your application likely would have been approved, or reducing your existing debt by X amount could change the outcome. It gives actionable feedback.
That's really useful for the person getting the decision. It sounds like all three approaches, post-hoc, intrinsic, and human-centered, are crucial pieces of the puzzle.
They really are. Each addresses explainability from a different, valuable angle. And the paper then moves on to discuss the key results and findings from research using these techniques.
Okay, so after surveying all these different methods, post-hoc, intrinsic, human-centered, what are the main things researchers have actually learned or found so far? What are the big takeaways?
Well, one of the main findings, maybe unsurprisingly, is that the paper really confirms the significant potential of LLMs. They really can enhance AI explainability across a huge range of applications using all these different methods we've talked about.
So it's not just hype. LLMs are proving useful here.
It seems so. They're emerging as a genuinely powerful tool in this quest for more transparent AI. But, and this is a big, but the paper also strongly emphasizes that just generating explanations isn't enough.
Right. You need to know if they're any good.
Exactly. We need robust ways to evaluate how good, how accurate, and how useful these LLM-generated explanations actually are. Evaluation is critical.
And how do researchers go about judging that? How do you measure the goodness of an explanation?
The paper discusses a few ways. There's qualitative evaluation. This is more about human judgment.
Like asking people if it makes sense.
Pretty much.
Yeah.
Does the explanation seem comprehensible? Is it clear? Does it feel satisfying to the user? Researchers might conduct user studies, asking people to rate explanations on clarity, helpfulness, things like that. Another qualitative aspect is controllability. Can the user interact with the explanation? Maybe ask for more detail on a specific point, or ask the LLM to rephrase something that's unclear. That interaction potential is important.
So it's about the user experience. What about more objective measures? Quantitative stuff.
Yes, quantitative evaluation uses metrics you can actually measure. Two really important concepts here are faithfulness and plausibility.
Faithfulness and plausibility. What's the difference?
Okay, faithfulness measures how accurately the explanation reflects the actual reasoning process of the original AI model. Does the explanation truly represent why the AI made the decision it did, based on its internal workings?
So is it telling the truth about the AI's process?
Essentially, yes. Plausibility, on the other hand, is about whether the explanation makes sense to a human, particularly an expert in that field. Does it sound reasonable? Does it align with known domain knowledge?
Ah, okay. So an explanation could sound good, sound plausible,
Right, it could sound perfectly logical to a doctor, for instance.
but not actually reflect what the AI really did.
Exactly. The paper makes this crucial point. An explanation can be plausible, but not faithful. It might offer a believable story that doesn't accurately capture the AI's potentially flawed or complex reasoning. And ideally, you want both.
That's a really critical distinction. We need explanations that are not just understandable, but also true to the model. And the paper mentions data sets used for this, for training and testing.
Yes, absolutely. The paper discusses several important benchmark data sets. These are crucial for progress because they provide a common ground for researchers to train their LLMs to generate explanations and, importantly, to evaluate and compare different methods.
What kinds of data sets are we talking about?
They test different things. Some focus on logical inference, like the ESNLI dataset, which has pairs of sentences and asks the LLM to explain why one sentence entails or contradicts the other. Others focus on common sense reasoning, CoSE, ECQA, scientific knowledge, World Tree, Open Book QA, or grounding explanations in external documents. Explain LLM, Yak Bench. There's even one called Hate Explain, focused on explaining hate speech detection without bias.
Wow, a whole range. So these data sets help push the development of better explanation techniques.
Definitely. They provide the challenges and the yardsticks to measure progress against.
And the survey also highlights real-world applications where these LLM explanations are making a difference.
Oh, yes, absolutely. The paper showcases a really wide range of practical applications. We've touched on some already. In healthcare, think explaining diagnoses like linking fever and cough to potential pneumonia, or helping researchers understand molecular interactions for drug discovery.
Okay.
In finance, explaining credit risk assessments, flagging potentially fraudulent transactions and explaining why, or analyzing factors driving currency trends.
What else?
Applications in law, like reviewing contracts and explaining why certain clauses might be risky or non-standard. In manufacturing, explaining predictions about when a machine might need maintenance. In education, explaining personalized learning recommendations. Even urban planning, explaining models of traffic congestion.
It's incredible how broad the potential impact is. Just making these complex systems more accessible seems to unlock value everywhere.
It really does seem that way. Building trust and understanding is key to adoption.
And I think that outline mentions something about comparing different LLMs, like ChatGPT versus others.
Yes, that was an interesting part. The paper included an analysis using something called saliency maps. These maps basically visualize what parts of the input data the model is paying most attention to when making a decision or generating an explanation.
Like highlighting the important bits.
Exactly. They compared several different LLM architectures like ChatGPT, Llama, V2, Cohere, Mistral, others, and found that they sometimes emphasize different features, even when looking at the same input.
So different models might see the problem slightly differently.
It seems so. It depends on their size, their training data, their architecture. The analysis suggested, for example, that models like ChatGPT often showed high saliency on critical features, meaning they were quite good at focusing on the important parts for the explanation. But there was definitely variation.
That gives us a peek under the hood, not just at the AI being explained, but at the LLM doing the explaining. So, with all this progress, it can't be all smooth sailing, right? What are the remaining bumps in the road? The limitations and challenges?
You're absolutely right. It's definitely not a solved problem. There are still several significant challenges and limitations the paper points out. One huge one is sensitive data.
We touched on this with healthcare, privacy concerns.
Yeah, exactly. In fields like healthcare, finance, even HR, the data needed to generate truly insightful explanations is often highly personal and private. Think about explaining an ICU mortality risk prediction. You need detailed patient data.
Yeah.
Finding ways to access and use this data for explanation generation while rigorously protecting individual privacy is a massive technical and ethical challenge. We need robust security, anonymization, maybe new techniques like federated learning for explanations.
A tough balancing act. Transparency versus privacy. What else?
Another big one is societal diversity and norms. AI models and the LLMs explaining them need to be sensitive to cultural differences.
How so?
Well, what's considered a normal or expected pattern, or even an acceptable explanation, can vary hugely. Think about medical conditions. Prevalence differs across populations. An explanation that makes sense in one cultural context might be confusing or even offensive in another. Even simple analogies or metaphors used in explanations might not translate well.
Like the thumbs up gesture meaning different things.
Exactly that kind of thing, but applied to how AI explains complex issues. We need models that are culturally aware and explanations that are adaptable, avoiding unintentional harm or misunderstanding.
That's a really subtle but crucial point, especially as AI goes global. Any other major hurdles?
Yes, dealing with multi-source data. AI systems often combine information from wildly different places: social media trends, financial reports, sensor readings, clinical notes.
Right, a real mix.
Figuring out how to weigh these diverse sources appropriately, and then generating an explanation that accurately shows how each piece contributed, is really complex. You don't want the explanation skewed by, say, noisy social media data, when reliable financial data was actually more important for a credit score.
Making sure the explanation reflects the true drivers. Got it.
Then there's the sheer complexity of the AI models themselves, especially deep neural networks. Even for experts, fully grasping the intricate decision-making pathways can be incredibly difficult.
The very problem XAI tries to solve is also a limitation for XAI itself.
In a way, yes. And designing interfaces and explanation methods that work for different users, from domain experts to casual users, is a huge challenge in human-computer interaction.
And computational cost.
Right, that's another aspect of complexity. These big models, both the ones being explained and the LLMs doing the explaining, need a lot of computing power. Deploying them on edge devices like phones or local sensors can be tough. Techniques like knowledge distillation are being explored.
Where you train a smaller model to mimic a big one.
Exactly. Like training a smaller DistillBERT to act like a bigger BERT model. It's a way to get efficiency, potentially making explainable AI more deployable, but you might lose some nuance.
So performance versus explainability versus efficiency. Lots of trade-offs.
Always trade-offs. And one last major challenge we have to mention is bias and fairness within the LLMs themselves.
Ah, yes, if the explainer is biased.
The explanation might be, too, LLMs inherit biases from the vast amounts of text data they're trained on. This can manifest as social biases like gender stereotypes in job recommendations, language biases where performance is much better in English than other languages, or representation biases where groups underrepresented in the training data get unfair or less accurate explanations. Mitigating these biases in the explanation generation process itself is a huge area of active research.
So many layers to consider. Okay, despite these challenges, the potential applications seem vast, as we discussed earlier, across many fields.
Absolutely. The potential is still enormous, driving a lot of this research.
Well, this has been a really insightful deep dive into how large language models are trying to crack open those AI black boxes. To wrap things up, what would you say is the single key takeaway for our listeners today?
I think the main thing to remember is that LLMs offer genuinely powerful, promising tools for tackling this critical black box problem in AI. The goal is fostering greater understanding and ultimately greater trust in these systems as they become more capable.
Right. By using those different approaches, looking back after the fact, building explainability and really focusing on the human user.
Exactly. We're making real progress in understanding how AI arrives at its conclusions, using these LLMs as translators or guides.
And we've seen how crucial it is to evaluate these explanations. Are they just plausible, or are they actually faithful to what the model did? That distinction seems key.
It really is. And while this survey paper gives a fantastic snapshot of where the field is, it's vital to remember this is moving fast. It's a very active area.
Lots of research and development still happening.
Definitely. There are still those significant challenges to overcome: data privacy, bias, complexity. But the potential benefits of getting this right, of having